Okay, so the next piece to like solving polynomial equations, and actually I should say solving them, efficiently, is knowing what the potential rational roots theorem says. Because we have a remainder theorem, so if we know we have a factor, we find a zero, it divides out, and we can reduce it. So that's great. But where do these zeros come from? Like if it's just guessing and checking, is there a logical way, or is there, a systematic way to find them without a graphing calculator? So that's where the potential rational roots come in. If it's going to have a rational root, and remember, a rational root would be any number that could be written as a ratio, like a over b. So we could think like integers, like -4 or 2 or 0, like those would be rational roots, or even like fractions like 1/2 or 3/4, anything that's a ratio. If it were to have a rational root, then you could list out the potential ones. So like of all rational roots, like of all rational numbers, I should say, you don't have to check an infinite number of them. There's a finite number that you have to check, and that's why it's called potential. It doesn't guarantee it, but at least it narrows down the field to a finite few. Okay, and again, you probably covered this in Ha2 last year. So you need to look at what your P's and Q's, like mind your P's and Q's, right? So if you look at P would be if you have all the factors of the constant term, and Q would be all the integral factors of the leading coefficient. So you list out your P's, all possible factors, list out your Q's, all possible factors, and then really your potential rational roots, which would be the zeros, would be the ratio of every possible P over Q. So there are, you still have several to check, and that could still be a significantly large number, but at least it's a finite number. It's not an infinite number of values. So if that's the case, so if I look here, I see a -2 and I see -3. So if I want to know what are all my P values, they're integral values of -2. So off to the side, I could say P could be ±1 or ±2, because those would be values that divide into -2. My Q would be all the values that are integral factors of -3. So that's ±1 or ±3. And then what I have to do is think about all possible ratios of P over Q. So it could be like 1 over 1, 1 over -1, 1 over 3, 1 over -3, 2 over 1, 2 over -1, 2 over 3, 2 over -3. So my P over Q values would be, and I always like to say plus or minus, it could be ±1, ±1/3, ±2, ±2/3. And I think in Ha2, one of the teachers even does like plus or minus factored out, like a 1, 1/3, 2, 2/3. That's fine, right? So those would be the potential rational roots. Now, so there are 8 of them. So instead of trying every single value that's a rational number, I would just have to try 8 specific values. And if I have 8 values to choose, I maybe quickly I can determine, would one of them be a 0? And if none of these 8 work, then it doesn't have rational zeros. It might have irrational, like a square root of 13, but at least I would know that there's not rational ones. Now, part B is a bit tricky, because initially you might say your p-value is ±10. Well, that's right, but also wrong, because this isn't the constant term, right? That's an x. So before I would figure out that that's the constant term, I'd have to first factor an x out, because I knew that would at least be one factor, divide that out, so at least I know that this tells me that x equals 0 is a solution, which is rational. But then, you never would have gotten that from a potential rational root, P over Q. So now that I factor that out, so I do have a constant, my p-value would be plus or minus the factors of 10. So 10 plus or minus 5, plus or minus 2, plus or minus 1. And then Q would be plus or minus 3 or plus or minus 1. To get P over Q, you look at all these possible factors. So my P to Q would be plus or minus 1, plus or minus 3, oh wait, sorry, I went that backwards. I apologize. Plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 5, plus or minus 5/3, plus or minus 10. Sorry, I got really messy. And plus or minus 10/3. So again, it's a lot, but it's still a finite number. Okay, so now let's see these in action. Let's solve this. And when I'm solving this equation, I need to realize that a fourth degree polynomial, that's really hard to factor if I don't see factor by grouping. Like there's no formal process like factoring a quadratic or using quadratic formula. So what I want to do is think about, well, if this were to have rational zeros, and I'm going to call them quote unquote nice zeros for now, I would list out my P's and Q's. So I'm going to go a different color. So P would be all the factors of -8. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And Q would be just plus or minus 1. So when I divide my P over Q's, notice I'm just going to get all of these values as my rational roots. So I have that are potential rational roots, I should say. So I have 8 to choose from. Now, you don't have to always start with like the most complicated one, and you could try to guess like, oh, I think it's this. So I'm just going to do a shot in the dark and say 2, and I'm going to say 2, and I'm going to use the remainder theorem by doing synthetic division. So I'm going to lay out my coefficients here. So 1, -1, 2, -4, and -8. And I think 2 is a 0, so I'm going to put my 1 down here and see if I get a remainder of 0. So 2 times 1 is 2. Add, don't forget we're adding, that's a 1. 2 times 1 is 2. Add is 4. 2 times 4 is 8. Add is 4. 2 times 4 is 8. Add is 0. Wow. I'll be honest with you. I actually thought I picked a 0 that wouldn't work. So that kind of backfired. I got lucky. It worked. So that's wonderful. If you're not so lucky, then you just erase and you try another one. So, if I would have tried, if I would have tried -2, let's say I would have tried that. Oh, actually, I'm going to do that over here. So let's say I would have tried -2. Okay, and I would have divided that into 1, -1, 2, -4, -8. So I bring that 1 down. -2 times 1 is -2. Add, don't forget we're adding. That's -3. -2 times -3 is 6. Add, that's 8. -2 times 8 is -16. Add, -20. -2 times -20 is +40. Add is 32. Okay, no bueno. I know that this is not a 0. So then I just have to try another one. But I found that 2 is a 0. That means that x minus 2 was a factor. That also means that I've reduced a fourth degree to a third degree. That's x cubed plus x squared plus 4x plus 4. And now I want to try to factor this. Or if I don't know how to factor it, I can use synthetic division again and try another 0. But I'm noticing that I can group this. I can factor by grouping. I'm going to pull out an x squared out of the first 2 terms. And that gives me x plus 1. I'm going to pull out a 4. And that also gives me x plus 1. And remember, I still have this guy here. So I have x squared plus 4 times x plus 1, and then remember we still had this x minus 2, all equal to 0. So as I start solving, I now have a really easy way to solve this because I just found those zeros, and I know that here, right, it's x equals 2 is our 0. Here, x equals -1 is our 0. And here, it's technically plus or minus 2i, but it does say only solve in the real number system. So if you did pick up some irrational values, imaginary numbers, we don't we won't include them today, but in the next section we will. So this one only has those 2 zeros. Okay, so I really like that example. And again, kind of go through, revisit that as you follow along, look at your notes, and rewatch that. But synthetic division is going to be so helpful. So if again, if you're a little bit rusty on that, make sure you go back and try to be able to efficiently go through that for tomorrow's class.